So in this video, I'm going to explain how you can design a dipole antenna. So what all the practical issues will come when you design a dipole antenna. So I'm going to explain a little bit theory of this dipole antenna. So it's a simple form of dipole antenna. So anybody can design this dipole antenna. So if you have any requirements, like if your Wi-Fi range is less, so and you needs to put your antenna a little bit far away from your Wi-Fi, then you can purchase some coaxial cable and you can yourself make some dipole antenna and put it on the Wi-Fi modem so that the reception will be increased. And the second application, maybe this will be the day-to-day life application will come if your laptop has less range, and you can open your laptop and connect this antenna to external, so you can increase the range. So the dipole antenna is one of the good and good antenna, so you can uh, design this antenna yourself. So I'm not going to explain much into the how you can do the simulation, but I can provide you some tips how you can do proper simulation. And I'm not going to much into the theory. Have some graphs of with that graph you can find out this dimensions easily with your tools. So dipole antenna will be like this. Two elements it has, two wire it has. So maybe cylinder wire we can take. So the distance is a length L, and usually it is connected. One is connected to the outer conductor of the coaxial shield, and the next one is connected to the inner conductor of the coaxial shield. So this is this is the input impedance of the dipole antenna. So it's not much required in our design actually, but from this we will understand how we can create a good we can identify a good length for our dipole antenna. So what will happen if I use different kinds of length, whether this efficiency will increase, or what happens that you can identify from the this equation. That's the main thing for this equation. So usually in all these graphs actually they represented as a lambda. So in all this length they represented as a either in degree or in pi in radian. So what does it mean by one complete cycle lambda? Lambda means the frequency which is working, which is for your application. Like if you are designing this antenna for a 2.4 gigahertz like Wi-Fi, then this lambda will becomes corresponding to the 2.4 gigahertz. So using this simple equations, you can convert it into lambda. So one complete cycle is called a 360 degree, and so for example, this will be lambda by 4. It's a pi by 2, half cycle pi by pi, and complete cycle 2 pi. So this is one good graph. So from this graph, what we can see is that this they put as a degree. So degree they mention. So one antenna is working good means the resonating it, which means the reactance part is 0. If you have some antenna or some RF, some antenna, even if the impedance is more than 100 ohm, we can still use if this reactance part is 0. Using some impedance converter like a more balance, we can convert from one impedance to another impedance. But the point is that if this antenna reactance part is 0, then it's a very good antenna. So uh, for the resonant part, we need to check in which length this reactance parts become 0. So from this we can see that it's 90 degree, this reactance is 0. So 90 degree means lambda by 4. So lambda by 4 is wire has a distance is very good. So you can do some calculations for 2.4 gigahertz or something. You can do the calculations and find out this length. So this graph is providing the resistance versus antenna length degree 90. So here is provided actually A is the length and D is the diameter. So what will happen if you have different diameter and the length parameters? So they put the A by D values here, and they put the length also here. So from this you will get some idea how your diameter of the wire is impacting your design. So if you have a different kinds of wire distance, then and so from this we can say that our antenna is 90 degrees good. So this axis 90 degree, so length is 90 degree, and this axis is the reactance. So usually the reactance will be much if you are not using any balun, any other equipment, you are plan to directly connected this coaxial cables to the dipole antenna, then you have to consider then this impedance should be comes within this range. So within this, so if you draw the curve graph, so 90 degree, so you will get the length something somewhere here, impedance somewhere here. It's maybe close to 60 ohm resistance, something like that. So from this we can see almost all the A by D distance, which means almost all the diameter you have the same resistance if this antenna length is a lambda by 4. So if you are designing designing very lengthy antenna, or maybe there are some applications sometimes you have to design the antenna with a different length. So in that case you can see the difference of the reactance, how this resistance is changing. So in the same time the reactance also is changing. So at that time it means even the length is changing, the efficiency of the antenna is changing. So this is actually what is meant by is indirectly saying, if you have a big length harness, in case of EMC it's not creating much issue, because when this length is increasing, that time the resistance both resistance and reactance are changing a lot. So only 90 degree only it's providing more performance. Only the 90 degree means lambda by 4 distance only it's providing maximum radiation efficiency. So this is also very good. So in and again going to above high length, you can see this performance is varying, both reactance and diameter resistance. Okay, so from this graph, from these two graphs, you can this application is very large. As I said, this application is very large. This can be extended up to in EMC also. In all your calculations, you can apply these two graphs. How the efficiency of an antenna is. But in our case, our aim is to design a dipole antenna. How we can design a dipole? So from this, we know we can took any diameter. It's not a big issue, but the length should be 90 degree or lambda by 4 distance for each wire. Okay, so some case we don't have a cylinder. So all these equations you see is defined by a cylindrical wire. But in real applications, it may be difficult, because sometimes you need to design the dipole antenna in a PCB. So that time you don't have the diameter. You only have the width of the trace only, and maybe the thickness of the trace only. So in that case you can use this graph also. So this will be your means this will be your conductor or your wire or something, your boom, this metallic shape. So this is the cross section. So cross section, this is a thickness, and this is the S, this is a this thickness, and this dimension. So here they in this graph, this is T by S, so this ratio, and this will be this axis is the equivalent radius of the uh, metal. So how we can put in, so S will be, so here also they divided by the equivalent radius by S. So we know S and T from our means actual measurement. Then you can calculate equivalent radius. Then you can again go to this for instead of going to the formula, you can directly go to this, and you can find out the impact, or you can directly go to the formula also, you can calculate everything. The second case, based on the based on this length also, this radiation pattern is changing. So radiation pattern in the sense, this antenna is radiating power to 3D shape. All the axis it's radiating into all the spaces, but it's not equally it's radiating. It's changed, means it's changing. So they put the radiation pattern. So from this, what I can say, this will be. So the antenna is actually placed like this. So antenna is actually placed like this, and this will be, maybe this is for only for your understanding. This will be the coaxial cable, and it's connected here, connected here. So this will be the lambda by 4. So in that case, so the radiation pattern will be look like this. So what does it mean by there is no radiation this side? There is no zero. Theoretically, it's zero, but practically there we can see some radiation, and this will be the maximum radiation area. And when you increase this length a little bit, this maybe becomes like this area. In practical application, this area you can say a little bit high gain. So usually the gain will becomes around 2.1 dBi, and this directivity I think it comes around 1.6. So this is a very good antenna. As I said, this is a reference antenna usually used in most of the antenna peoples to validate the other antenna. And this is the different length, based on different length, the antenna radiation pattern is changing. So as I said, there may be some case. So if your application is like you need a high gain at this direction, so that time you can plot. This is a 2D graph. This is a 2D graph. In actual case, this will be the dipole. This will be the dipole antenna. So the pattern will be look like this. So it look like this. So you can see it's like a ball. It's like a ball, and two side, this area and this area, there is zero. There is no radiation theoretically. So it will be like this. So yeah, maybe you can take like a apple. You can think like an apple. So maybe their radiation patterns looks like this. And if you cut the apple, then in this axis, then that they plotted like this. So this axis is, I think they plotted. It's theoretical calculation only, and the equation will be like this. So this is the theory. From this theory, you can do some initial analysis how it will be designed. But in and the next stage, usually you have to, or you will go for the simulation. So I will explain to you what will happen if people are doing wrong. So the thing is that you should not go to the simulation part after designing this. You have to think how you are going to fabricate this, how you feed this. So usually people are feed by the yeah, as I said, it's feed by the coaxial cable. So they put long coaxial cable, and center conductor is connected to the one, and another conductor is connected to the. So this will be the theoretical case. But in when you fabricate this in there is some issue. So then what people usually do, they directly went to either in 3D simulation like HFSS or CST, and they draw the tube through two wires like this, and they either they put the lambda port here, and they do the excitation here in lambda port. So the issue is that when you feed like this, that time it's a perfect feed. There is no balance issue is not coming. So in actual case, this is a balanced shape, and the coaxial cable is most of the time is unbalanced, or it's unbalanced. So what happened is that uh, the current starts to flow, and it's some current will also always flow through the shield of the coaxial cable also. So what happened is that the problem is that we expect the radiation pattern is like this, perfect radiation pattern, but in real case the pattern may be distorted like this, because of most of the currents maybe go through, or half of the current maybe go through the shield, because the balance issue, so the field is not matching with the field in the antenna. So that time the radiation pattern is different. So that you can easily identify it when you fabricate this antenna. When you place your hand close to this antenna, the performance of the antenna is changing, the impedance of the antenna is changing. So maybe some people directly concluded that they will say the theory and the simulation is wrong. But the actual issue is how they simulated. The simulation is wrong here. There is no consideration. They are not considered anything related to the modes. So that is the issue here actually. So the the best options to get the actual performance of the dipole by directly putting the same coaxial cable also here in the simulation. So in the simulation you model the coaxial cable. So almost no needs to model a lengthier cable, but if you're planning to model a cable approximately like this distance, then you have to model the cable also here. Then you have to feed this antenna, and here only you needs to excite. So and I prefer use wave port and close the wave port also by placing some metallic sheet here. The reason is the wave port because if the frequency is increasing a lot, if this coaxial dimensions itself compared to lambda, and the coaxial cable itself containing more modes, so that time there is a chance again your simulation may be wrong. When you do the simulation fabricated again, this pattern is different from this. So for this, so this is the just theory I put. So to solve that issue, what you can do is that you can put a balloon, put a balloon here. So balloon prevents. I will explain the theory of the balloon in another video. So the balloon will block this currents going to the shield. So it's provide high impedance for the currents which go to the shield. So usually all the currents is forced to go only this direction, only this. So that time what happen is that the pattern you will get the pattern again in the expected pattern. So type without if you are feeding your dipole with a coaxial cable, you have to consider the balance. Okay, so balance design of balance again difficult. So what you can do is that you can put ferrite cores in the shield and place it close to here. Not for the feed, because if you put it directly on the feed like this is if you put the ferrite here on the feed, this ferrite core is attenuate the signal is going to the antenna, so your gain will be reduced. You have to put the ferrite bead here, sorry, not the bead, ferrite core here, and so that this will reduce attenuate the currents which is going to the this, or not only attenuating, it will provide more attenuations to the more impedance to the currents going through the shield. So again this push the currents to actual and this also you will get some good, but always balance is the good because it's not attenuating the signal. And okay, so still these two things are difficult. So again some of the things that people usually do is that, so instead of putting the coaxial cable here, so they have one element here and they have another element here, and the coaxial cable come from here, and they remove the shield from here of the coaxial cable and solder it. So so still okay, as I said, the current will be go through this shield. Still also the current will go. So when you took the parent, maybe the parent may be so this is your axis, and if you took the parent, this may be something like this. More the more power is radiating into this direction. So what you can do is that so reduce this as this element length, cut it. So we are deviating from the initial decision design. So as per this theory, both are same, but for these things I saw in some antenna people are doing, cut this. So what happened is that the efficiency of this current is reduced. So the pattern will become again symmetrical. Okay. So always balance is the good, but this is also one of the thing. And the thing next, you can also so if you are working for a 2.4, then this will also you can make some connections. Uh, I also I see people are do some kind of connections like this shorting. it's directly feeding, and maybe this also reduce the means differences in the radiation pattern. So using this kind of techniques you can change the radiation pattern. So summary what I can say from this equations, you know the theory, how the impedance is different, and why how the patterns will difference changing, and what all things you need to consider in the simulation. So in actual simulation also you try to implement actual things also. And the next thing is, usually this is a floating thing, so there is a chance this can be directly charged up, static charge or direct EC discharge. So always try to provide a DC short between these two by providing an inductor. So so using this inductor you can provide the DC short, and that will help you protect from the static charge as well as the ESD. So this is the basic, this is the little knowledge which I have in the dipole. From this you can, and like some adjustment, you can design the dipole itself. So sometimes you need only one conductor, and the shield will be act like a second conductor. So maybe with one thing itself you can create the dipole antenna. So I will come back with the design of different kinds of balun, and in the later video we can see how we can design different kinds of the antenna, and how we can do extend this simulation and the design also. So from my perspective, for the dipole antenna design, there is no need for the simulation, because always you see this length will be always less than lambda by 2. So don't needs to go and design an antenna with lambda by 2. Always there these elements comes with some resistance. So you will get it. So the length will be almost comes around 80 degree. So 80 to 90 degree this length will come. And you can okay, then you okay, and the next, so I missed something. So you fabricated all, you consider all things, and you can design the balun and everything still, and everything is without designing the balun. So you designed everything, still also your VSWR or the return loss means still also the efficiency is less. So that time what you can do is that you can adjust this gap you can adjust and do the impedance matching by adjusting the feed. Do not increase, so this length should not increase. This should be as small as possible. As small as possible. This should be placed as small as possible. And by adjusting the inductance and the capacitance, you can match your antenna. Even though you can you can, even though if the height is increased, so the total length is increased, you can doing some feed adjustment, you can match these sections to zero reactance. Okay, so that's all. I think that's all the uh, design of the antenna. If you have any questions or queries, you can put the comments below. I will come up with more antennas and more designs in coming videos.